Just a little bit about my background. Last 10 years have primarily been in service development at Nike. Before the data science platform, we were powering user experiences like the Nike.com website or the Nike apps with machine learning recommendations. So largely in the product recommend or personalization space. Along with that, we also had the task of essentially operationalizing the models, maintaining them in production and whatnot, and we developed some tools to make that an easier, seamless process, which is what spun off this data science platform. Before Nike, I worked at UCLA doing medical imaging studies for about 7 years, so that gave me a lot of great exposure into the scientific method, how science is done against data, and a lot of insight into how data scientists do their job and operate. So first, I kind of want to just outline the problem that we were solving here. Fundamentally, scalability was the problem we had. We needed to be able to scale both vertically and horizontally within Nike to drive data science in the organization. Horizontally, we needed to be able to onboard new data scientists, new data science teams, ensure they were productive, and vertically, we needed to add efficiency into delivering machine learning models into production. It was a pretty expensive process to go through, and we needed to bring that cost of an individual model down to open up new use cases, accelerate A/B testing, address all the kind of lower ROI use cases that we had for data science. So that was our problem, was that scalability thing, scalability issue. To achieve that scalability, we realized fairly early on that a DevOps approach is going to be necessary to scaling that. You've heard through a number of presenters today that the throw it over the wall, the handing off the code is not scalable. It would take weeks to be able to do that, and it's a one-way process, and you couldn't continue to iterate and develop that modeling code by throwing it over the wall. So the DevOps process enables people to bring their stuff into production and own the lifecycle of that code throughout. Additionally, we wanted to accelerate all of the aspects of data science in that modeling use case as well. So some of the constraints that we had to work with was primarily organizational. Nike has many data science teams, and they all have very different makeup. We have large teams of data scientists that are essentially siloed. They don't have embedded operations people. They don't have embedded engineers. We have some teams that have the embedded operations people in addition to engineers. Then we have some teams that are primarily just traditional service engineers who have data scientists on their team to kind of complement their domain that they're working in with data science. So we had to create a tool set that's going to work for all three of, at least three of those different team makeups. Additionally, we needed to make sure this platform reflects how data scientists currently work. We didn't want to change the tools and technologies they were using. It should be able to work in the platform that they're currently using so that they don't have to change too much of how they get their job done. Lastly, it needs to be easy to use. Data scientists shouldn't have to be engineers to get their job done, and teams of data scientists shouldn't have to hire engineers as well. The use case and the problem domain of this machine learning pipeline can be simplified and generalized enough that it can be made easy enough for data scientists to consume the tools on their own without leaning on engineering. And last, I kind of want to frame the context of this presentation. It applies to the training domain, not the serving domain. So training, I kind of mean the arbitrary data processing use case. You're reading data from storage, processing it on a resource, writing the data back to storage, whether it's a batch of data or a model artifact, whatever it is, that is what I would consider the training domain. And with the context of data scientists owning the life cycle, that's where their responsibility ends, is writing the code that can produce that model artifact, ensuring it's running on a scheduler, an ad hoc basis, and being responsible for that artifact being accurate. That's what we consider their responsibility, and they own the life cycle of. Slightly tangential to this conversation, but the serving domain can actually be completely abstracted and just handled by engineering without having too many constraints on that training domain itself. So that's sort of where their responsibility lies. So here's kind of what our transformation was at Nike by implementing these patterns and what we built in this data science platform. Initially, it would take weeks to productionize a model, whether productionization would mean it's scheduled in Airflow or ready for ad hoc executions, potentially by other services or programmatic executions of that modeling pipeline, to where now data scientists can put their model into production, and in the sense production just means the pipeline's ready to be executed and it's being executed by a scheduler like Airflow or through some other programmatic invocation of that modeling pipeline. They can do that in minutes now. Development, once development was done, data scientists could only run one of their models at a time in production. So if you have a model name, only one data scientist could run that model in test. So essentially they had to synchronize all of their test use cases in that test environment one at a time, to where now we have any number of concurrent dev and test executions going on, where in addition, the development executions are all scoped by their individual user, so you have no risk of collisions of data. If someone else is executing that model, you don't have to go and synchronize with them saying, I need to do some testing on it. You can just execute your model with confidence, knowing that you won't collide with anyone else's data. We had difficult reproducibility. In development, it was almost impossible to revert back to a version of code and data and parameters that might have led to a particular outcome or a particular accuracy. Conversely, in test or production, if you had a failure and maybe a day or two passed before you could debug that failure, it was very hard to replicate that state of that failure, to be able to replicate that issue, to be able to fix it. To where now both of those cases, you can replicate any one of these pipeline executions within minutes without even being familiar with the code base. You can just check out the model, execute it with that failed execution against the same data, and you'll be able to replicate the issue. So it made maintenance much easier as well. We had limited monitoring of failures in the pipeline itself. So if there was an Airflow processing failure, you might get an email. It's often one of many emails you might get from Airflow, so you ignore all of them until a downstream user of that modeling artifact might make some noise saying it hasn't been refreshed in 3 days. And we also had no observability of metrics themselves. So we couldn't say what is the accuracy of this model or this collection or domain of models at any given time without a bunch of manual work. Additionally, we couldn't action on failed metrics or failed alarms. To now, we have a catalog with the alarms and the metrics. We get Slack messages when a metric threshold is crossed. We get Slack messages when a pipeline has failed or an SLA has been missed. Additionally, we had many different one-off CI/CD pipelines. Even within a team, each modeling use case would vary just a little bit, that CI/CD pipeline was a little bit different. To some data science teams who weren't doing any CI/CD as well. So along with this, we sort of implemented just a good software practice pattern where you do your development in development, push it to a branch, run your pull request analysis on a branch, get approvals, push it to production. And then the next execution of that pipeline is going to be executing the new code there. So just to touch on real quick how this platform addresses these 3 phases of data science. Development, you're going to have your parameter, code, and data tracking. So that means every execution of a step in a model pipeline you do is implicitly tracked for reproducibility. So you know the code, the parameters, and the data that led to what outcome. And that's going to be accuracy or modeling artifact itself. So it's very easy to replicate executions you might have done hours or weeks or months before with confidence. You want to be able to support your parameter tuning use case, your hyperparameter tuning in an offline mode where you can set up your grid search and whatnot and just walk away from it and come back with your optimal parameters later. You need to be able to execute the entire pipeline in development. You shouldn't have to push your code to the test environment, execute your pipeline there just to go back to development to find an error and then push it back to test. You should have execute in local development the same way it's executed in test and production to give you that quick feedback loop at development time. Additionally, we need to have user data isolated executions. I need to have confidence that the data I'm producing from my development is not colliding with anyone else's data and vice versa. Productionization, once you bring your model pipeline to the test environment, it needs to be consistent and easy to test that model in that test environment. I'll touch on this a little later as well, but when you make changes to a modeling code base, you need to be able to run analytics and reports and whatnot to be able to show how the changes you made in that modeling pipeline affect your metrics like processing time or accuracy or number of users that receive predictions and whatnot, and be able to compare that to what it's doing in production. So if I made a change and my model accuracy just dropped to 15%, I can compare that to the exact same execution with the same data in production and see what that accuracy is. So now you have confidence that you can merge your code into production without issues. We need to be able to bring that pipeline into an executor. So a scheduler like Airflow is going to need to be able to execute that pipeline automatically, or it needs to be available for ad hoc executions. So an ad hoc execution would be a user manually invoking that modeling pipeline. Maybe they send a parameter of a new product that they want to generate an audience for, or it could be programmatic invocations of that modeling pipeline. You might integrate this modeling pipeline with other web services and APIs at Nike, or maybe you have an S3 sensor that invokes the pipeline. That pipeline needs to be registered for these ad hoc programmatic executions as well. And then standard comprehensive CI/CD pipelines. For operations, we want to have a seamless model catalog, which is also automated through this tool. We need actionable metrics. If you create a model, you own the life cycle of it. There's not going to be an operations team to let you know when there's failures. You need to know when steps fail, when pipeline SLAs miss, when accuracy drops below a particular threshold, and you just need to be notified of these events. You're not going to go and take a look at every execution every day. It's not realistic. So you want to have this notification for failures. So it's kind of the three phases that we try to address to accelerate that ML development at Nike. So how do we get there? We started with the pipeline. We found that this Airflow pipeline was generally the point in the development process that demanded this operations team. Within this Airflow pipeline, they're wiring the steps together, but really they're integrating that modeling code with the enterprise. They're going to have dependency sensors on other data processing jobs. There might be artifacts from your respective CI/CD pipeline in this modeling pipeline. You might have your alarming in this modeling pipeline. You might have some logic for reproducibility or some sort of transactional data within this pipeline. And this was generally the responsibility of the operations team, who happened to be us at the time, and we did not enjoy doing it. So that's why we wrote these tools. We needed to simplify that modeling pipeline. So we were able to go from initially hundreds of lines of one-off Airflow code to just simple declaration of the order of the pipeline, just the steps by name that you execute within the pipeline. So now this modeling pipeline is represented simply by the name of the step to execute and what it depends on. So on the left there, in the model steps configuration, you have 4 steps: ag users, ag orders, train, and score. And then on the right for each of those steps is just the step it depends on. So this would actually compile to be a DAG where the 2 aggregate steps run in parallel, it joins on train, and then it runs score. So now it's trivial for data scientists to declare and execute their modeling pipelines. Additionally, if you need to bring that modeling pipeline into something like Airflow, you just attach your Airflow scheduler information, and that Airflow DAG will compile to have those steps that you declared in your model steps in that Airflow pipeline. So now it's trivial for data scientists to create this modeling pipeline and execute it. But at the same time, that Airflow pipeline has a ton of information that's required to be able to execute that pipeline. So I'm going to go ahead and show how we were able to simply declare the steps to execute in that modeling pipeline. So first we realized all pipelines follow the same pattern. This is true for any ML pipeline, any data processing pipeline, any ETL pipeline and whatnot. You're going to have a state that the pipeline needs to wait on. which might be some upstream jobs that you need to wait on. You say it's scheduled at midnight. Once this condition is satisfied, which is going to be a job I depend on has completed writing its data for that day or that week or that month. You might have one or many of those. Once that condition is satisfied, then your data processing pipeline kicks off. So we kind of solidified around that pattern because it solved every data processing use case we had. Once that pipeline runs, each of the steps in the pipeline is going to run on ephemeral clusters. So we're in Databricks and Kubeflow right now, so we have fast resource spin-up. If you're on something like EMR or EC2, where you don't have that luxury of fast resource spin-up, you can follow a pattern of basically do a get or create on the resource, and you still have effectively ephemeral clusters, and you can rerun failed steps. So let me dive into a little bit what a step is. A step in the pipeline, I would say, is a checkpoint in the processing pipeline that you can rerun from primarily. So if you have a failed step execution, you don't always have to start from the beginning. Some of these pipelines can take 14 hours. If your post-processing step failed, you don't want to start over. It's a requirement that you need to be able to run any step individually and still be able to finish the pipeline. You might build a step if you have different resources that the code needs to execute on. Your data normalization might be on CPU instances, whereas your training might be on GPU instances. Then you need to decompose the logic into two different steps to leverage those different resources. And lastly, if you want to run something in parallel, you would make two steps, and those two steps can run in parallel. The DAG on the screen is a linear DAG, but we support it's a linear execution, but we support DAG executions just as well. So we started to build a contract around a step. So we can say every step of every modeling pipeline that's ever executed is going to be executed in the same way. It's going to have the resource to execute the step on, the code entry point to execute the step. And what we also did is we said all steps are parameterless. So that's how that pipeline declaration we had that did not have the parameters to each of the steps to execute. The reason it didn't have that is because every step for every model, for every pipeline is now parameterless. There's one parameter that's sent from Airflow or your ad hoc execution, which is going to be your run date. And your run date is ultimately the point in the data that you're executing your code against that's critical for reproducibility. So we solidified on that pattern. Now each of these steps don't have parameters. So how do we pass information from, say, a train step into a score step or an aggregate step, multiple steps into that last training step? There needs to be a mechanism to pass this information between the steps. That's what we call dependency resolution, and that's what made the pipeline stateless. We don't have this logic, we don't have this state in the pipeline anymore. It's just simple configuration. It's easy to execute. It's easy for any system to execute that pipeline because all it is just a few lines of configuration. So what we did is we created a library, an embedded library that data scientists consume in their data processing. This could be on Jupyter Notebooks, it could be on Kubeflow, it could be on Databricks. It's just a vanilla Python and Scala library. They consume that library to be able to pass information between the steps. So traditionally, the types of parameters that might be sent to a step are going to be your processing parameters or your I/O paths. Processing parameters are effectively hard-coded. They're registered in this library to be able to be tracked for reproducibility and hyperparameter tuning. But to a data scientist, your kind of hyperparameters, look-back data, those types of parameters are effectively hard-coded. We can rely on our comprehensive CI/CD pipelines to quickly make changes to parameters without having to externalize them in some Airflow configuration or some other source. Additionally, this way they're close to the code. There's no question about what parameters should I execute this code with. The next type of parameter is going to be your I/O paths. So usually your I/O paths may be passed from the pipeline executor, something like Airflow. Rather than passing them from Airflow, a data scientist simply calls a method on this embedded library and asks for an I/O path to write their data to, and then they give it a label. So if I'm writing some aggregated user data, I just ask the library for a path to write to. I write my user data there, I give it a label. Later on in the pipeline, I can reference that same data path Understand it's difficult to see on the screen here, but this is kind of a simple example of that code. That first aggregate step registers a parameter. It creates a data path called ag data. It's going to write its data there. When train runs, it needs to be able to read that data, but it needs to know where to find the data. So it's going to ask this embedded library to get the path that's been labeled ag data, and it's going to return the exact same path that train had just written to. So now what that did is that shifted all the state out of the pipeline into this embedded library so that we didn't have to make the pipeline complex and difficult to implement. All of your information passing is done within this embedded library itself. Additionally, you can create your metrics via this library as well. So a good example of a metric, classical example, is going to be your accuracy metric. Development time, I want to leverage that accuracy metric leverage that accuracy metric to track my outcomes during development. I want to know what data, what code, what parameters led to this accuracy metric, and I want to track that in development. Similarly, in production, I want to know when we detect model drift, when that accuracy drops below a particular threshold. So I'm going to register a metric around that and just track the accuracy. In production, what that means is when that modeling pipeline executes, you can set your high and low thresholds around it. Low threshold, low urgency threshold is going to mean I'm going to get a Slack message when that threshold is crossed. So a model that I own is in production just generated an accuracy of 20. I want to be notified when it's below 30%. So I would get a Slack notification saying that happened, but the step would still carry on. That artifact would still be used. If I had a high urgency metric, I might set it at 10%. That means I'll still get a Slack message, but also fail the execution of that step, and that model artifact would never make it into any downstream systems. That way you can set these metrics up and effectively just walk away from it and have confidence that the system is going to let you know when those thresholds are crossed. The last thing there is you have to call that the step is complete on the embedded library as well. Really what that's doing is just making the data that you had just written visible to other consumers. Until that step is done, we don't consider the data to be in a usable state, so we want to make sure no one else is reading it until that particular step is done. So calling complete makes it visible to consumers, and consumers being other steps within this pipeline. So how does that work? It's kind of the pattern we call dependency resolution, and this is sort of the cornerstone of this stateless pipeline. If people here are familiar with ML flow, it actually follows a very similar pattern to ML flow where every execution of that step is going to be publishing the metadata to an API. That's going to be the name of your step, the ID of that step, what your IO paths were, what your metrics were, what your parameters were. That gets published to an API. The only distinction is the data that's published from other steps is used as inputs to latter steps. And that's how we resolve things like IO paths, and we don't have to rely on the pipeline to pass that through. So the way the dependency resolution works is within your environment, within your test and production environment, for that model name, for that particular run date, it's going to take the latest step execution that has happened within that pipeline as long as they have a consistent object graph. So that they need to have consistent ancestry. So in the case up here where we have 2 steps that are run in parallel, then a train and a score and a post-proc, if you run them all in order, you will always get the latest execution of all of those. But if you ran 1, 2, 3, 4, and then you ran your normalization step again, and then you ran post-process, that second execution normalization would be discarded in favor of the first, because the first execution was used as an input to later steps, and you need to ensure that you have a consistent object graph of your inputs. So, for example, if your first step you generated your labeling data, you need to ensure that you have consistent labeling data throughout each step of that modeling pipeline. So this sort of guarantees that. If a user then reran train and score and then post-proc, once again you would get the latest execution of all of those. You can pin your executions to a particular run ID if you want to allow concurrent development of different steps. Conversely, I can actually source my data into another user or another environment through this mechanism, or test or production. If I only want to debug the post-process step, I can just source my post-proc step into production, but still have confidence that the data I'm writing is going to the test environment, so it's not colliding with production data. So the first concept in there is that this embedded client is providing the I/O paths to the code. That means data scientists don't have to be aware of the environment. They don't have to have an if statement that says, if we're executing a dev, write to this path. If we're executing a test, write to this path. And conversely, prod. This embedded library has knowledge of what environment it's executing in and is going to provide paths that reflect that. That way, the exact same code verbatim that you write in development will run in execution, but with different outcome, right to different paths. It certainly was not a difficult thing for data scientists to be able to know where to write their data, but it's just one less thing they have to worry about. And they don't really care where the data is going. They just need to write that data in the step and be able to read it in the next one. Beyond that last modeling artifact, that might have implications on the path, but everything in between, they don't really care about. We can just back it by buckets at TTL. 90 days later, the data's gone. That works fine. So that path that's returned is environment aware. So in development, it's going to be partitioned with my username, so we're not going to be colliding on data. Test and production, it knows the path for there. The important thing in this path is that step ID. So that's an auto-incrementing step ID for each execution. What that leads to is immutable data. So every time you're writing your data, you're never overwriting previous data. What that means is that if someone is reading that previous data, they're not at risk of reading incomplete data, and you have guarantees that the data you're writing isn't going to be consumed by anyone else until you have finished writing it. So you start to have transactional, reproducible data within your data lake as well. That has a lot of, at development time, that doesn't have too many implications except for reproducibility. In test or production, that means your data is always available, always accurate, always consistent, and you're never in a state of reading incomplete data, which unfortunately can sometimes silently fail. So I dove into the metrics a little bit. This is what the metric call looks like. I already explained that. I'm going to skip over it. What this also allowed us to do, since we have this consistent contract around every step within the modeling pipeline, is now we can have standard CI/CD pipelines. The pipeline is totally agnostic as to what the implementation of the model it's executing is. It just knows how to execute any arbitrary pipeline. And that allows us to execute that modeling pipeline on Jenkins in the CI/CD context and create these pull request analysis reports to surface back into the PR so that data scientists are quickly able to compare their branch changes in a test environment with their production changes, or with the same production execution. So what kind of results did we see in the organization through this effort? Fundamentally, it unlocked new use cases. We wanted to accelerate A/B testing, but the cost to bring a new model into production was far greater than any ROI we might get on any incremental A/B test. But we wanted to accelerate the A/B testing because in the long run, that's where you get the real value in the modeling. The single team, there's no more operations team. That's the biggest impact fundamentally that we had. Data scientists can own the life cycle. Additionally, they can own the life cycle, but their product people can make better product decisions now. When they can realize the entire cost of the project without externalizing all of your operations and maintenance costs, it's easier to make the case for a particular modeling project with that full cost and no externalized cost in mind. Reduce maintenance, so we can spend more time developing new use cases through this alarming and catalog. You can essentially just put it in production and not have to think about it, and you have confidence that you'll be notified if there's a failure. And additionally, we can onboard data scientists much faster. Every model pipeline is executed the same way with those parameterless steps. So I can just check out any modeling code base. The resource is part of the code. I can create the resource, execute the model without putting a single magic parameter into there. and have it complete and execute in my development environment with no side effects in test or production. Additionally, this gave us a single platform to focus our feature work in. We can multiply our effort. We could add a feature to the platform and immediately distribute it to 50 or 60 models across 10 different data science teams with the push of a button. So that's the impact that we had through this stateless pipelines pattern. So thank you, guys.